Hello. Welcome everyone to this deep learning session. So we are going to get started. So the first speaker having a long talk is Lucas Metz from Google Brain, and he's going to talk about understanding and correcting pathologies in the training of learn optimizers.
Thank you. Hello, everybody. My name is Luke Metz, and I'm going to talk about our work on understanding and correcting the pathologies in the training of learned optimizers. This is joint work with Niru, Jeremy, Daniel, and Joshua. In this talk, I'm going to go over some motivation for why we should care about learned optimizers, some problems we face meta-training them, solutions to these problems, and finally, a proof of concept learned optimizer. First, motivation. Recently in machine learning, there's been a trend moving from hand-designed to learned. For example, in computer vision, there is a shift from hand-designed features to learned features. We see the idea of meta-learning in line with how the field has been developing. Meta-learning involves shifting from hand-designed learning algorithms to learned learning algorithms. It took many years of hard work before it was clear learning features was better than hand-designing them. And we hypothesize meta-learning is in a similar state today. In this work, we focus on meta-learned optimizers. Optimizers have proven critical to the success of deep learning. But despite this, many of the methods used today are designed by hand. Methods like Atom, RMSprop, and SGD, for example. These all share the fact that they're relatively simple functions that operate on gradients and produce parameter updates. Instead of hand designing these functions, the learned optimizer community is interested in learning these functions. They define parametric optimizers and optimize those parameters to perform well on some task distribution. Sadly, however, training these learned optimizers is notoriously difficult. This paper is about understanding some of these difficulties and proposing solutions to them. Now, before I get into meta-learning, let's consider training a neural network with parameters W initialized randomly. To train a single iteration, we can compute some gradients to some loss, and then apply SGD. We can do this over and over and over again until finally we're done training. At the end of training, we can measure performance to see how well we did. This could be something like training loss or validation loss, for example. Now, meta-learning involves replacing this fixed form function that's SGD with an update function U, parameterized by some weights theta. To outer train, we can use our measure of performance to update the weights of our learned optimizer. We can then do this over and over and over again to obtain better parameters of our learned optimizer. The process of updating the learning algorithm's weights we refer to as outer optimization, or meta-optimization. We refer to applying the learning rule as inner training. In general, this outer optimization problem is quite difficult. It's expensive to compute a single function evaluation, requiring a full unroll of the inner problem. Function evaluations are also noisy and depend on things like initializations. And finally, the loss surfaces of these are quite complex, as they involve an iterative application of our update rule. As a result, the success of meta-learning-based approaches has been limited. The few successes we have seen require a variety of ultra-specialized tricks to make them work. There's been a lot of work exploring ways to do this outer optimization. One common family is black box methods. Techniques like random search, reinforcement learning, or evolution have been used. In this work, we're interested in gradient-based methods. We can think about training as just recursively applying our update function. Since everything is differentiable, we are free to take derivatives with respect to the measure of performance we care about. One promising method in the gradient-based family is truncated backprop through time. Instead of running a full inner training and backpropping the loss, we can split the sequence up into a series of pieces and backprop just along these pieces. For example, we can run 3 steps forward, run backprop, and then start the next 3 steps from where we left off. This is great because it gives us gradient information more frequently. We don't have to wait to compute the entire sequence. Instead, we can just run a couple unrolls and do an update on theta from that. Additionally, because these unrolls are short, the underlying loss surface is simpler and thus easier to optimize. Sadly, this truncation introduces a great deal of bias. The choice of unroll length thus leads to conflicting goals. Long unrolls are less biased, but are slow and have a horrible loss surface. Short truncations are fast and well-behaved, but suffer from severe bias. This leaves us with no great solutions. Now I'm going to talk a bit more about these problems. First, let's consider the bias introduced from short truncations. One experiment we performed to get at this bias is to meta-learn a learning rate. The inner problem here consists of training a 2-layer MLP on MNIST using Atom for 10K inner iterations. We use gradient-based meta-learning with different amounts of truncation, shown in the figure to the right. With low amounts of truncation, we actually see the learning rate decreases, whereas when training with full-length truncations, the learning rate should increase. What this means is not only will this bias lead to the wrong values, but it will actually move the learning rate in the wrong direction if the truncations are too short. The second problem we explored is exploding gradients. To build intuition, let's consider a simple 1D loss surface with 2 minima optimized with SGD and momentum. With low values of momentum, the iterate will converge to the first of the 2 minima. With larger values, we'll converge to the second of the 2 minima. We can visualize trajectories taken as a function of momentum, shown in the figure to the right. On the x-axis, we show inner iteration of gradient descent. And on the y-axis, we show the parameter value. With low values of momentum, shown in yellow, the iterate will converge to the first of the 2 minima. Higher values will oscillate and eventually converge to the second of the 2 minima. And even higher values will oscillate back and forth, eventually converging to one of the 2 minima. Now, despite being simple, these resulting trajectories are already quite complex. Now, I want to highlight that the y-axis here corresponds to a particular loss value. The first minima has a loss of around 5, the second has a loss of 0, and the hump between the two has a loss of around 11. We can plot this loss achieved after some number of SGD steps. For low numbers of steps, the loss surface is relatively smooth. But for higher and higher numbers, it becomes higher and higher curvature. To gain intuition why this is, consider the spike that occurs where the red arrow is. At this point, the iterate will either make it over the hump or it will not, resulting in 2 very different loss surfaces. For smaller numbers of steps, this is still a smooth function. But as we increase this, the loss surface becomes sharper and sharper. The iterate is either going to have settled in the first minima or the second. So this is a toy 1D problem. We hypothesize neural networks are also this sensitive to parameters of the optimizer. To show this, consider training a 3-layer MLP with Atom with slightly different learning rates, shown with color. What I show in this figure is the result of running PCA on these training trajectories. At initialization, all the models are the same. After 1 step, all the models follow a very similar trajectory. But after 10 steps, we start to see some of the models split off and diverge, going into different regions of the loss landscape. We can continue to take iterations and find that more and more models split away. Now, this just shows different trajectories. The ending positions of each one of these trajectories will have a slightly different loss value, resulting in outer loss landscapes, much like the toy example shown previously. Now, the types of learned optimizers we care about are a little more complex than a single learnable learning rate. We can follow prior work and parameterize our optimizer as a neural network and look at 2D slices of the resulting outer loss landscape as we vary the length of unrolls. These loss surfaces are with respect to changes in the learned optimizer's parameters and are what we're actually trying to outer optimize. For small numbers of iterations, the loss surface is smooth. But as we increase the number of steps, the resulting loss landscape starts to look more and more like noise. I want to highlight that this is the loss surface we're trying to use gradient-based methods to optimize. It's full of local minima and poorly conditioned, leading to exploding gradients. Now I'll talk about some solutions. To get around this crazy loss surface, we look to variational optimization. The core idea here is to define a distribution over parameters and optimize the performance over this distribution. This effectively smooths out the high-frequency structure of the loss surface. Now that we have our loss, we have a couple choices in how to compute gradients. We can use an evolutionary strategy style gradient estimator, which leverages the score function trick, or we can reparameterize the noise and use the reparameterization gradient. These two estimates have very different variances. If the loss surface is smooth, the reparameterization gradient will have a lower variance, as it scales much better with dimensionality. But if the loss surface has high curvature, the reparameterization estimate will have a much higher variance. To illustrate this, consider this cartoon loss surface. The reparameterization gradient estimator will be like averaging the green vectors, whereas the ES-style estimator, shown in blue, will behave more like a finite difference estimator, and it will ignore the local curvature info. Now in practice, these two gradient estimators are quite different. In the figure to the right, we show the variance computed over the course of outer training a learned optimizer. Over the course of outer training, there's up to 20 orders of magnitude different variance between these two estimators. Now instead of simply picking one, we can actually get the best of both worlds and combine them with inverse variance weighting. This is great because it'll give us an gradient estimator with the minimum of the two variances. In this work, we estimate each individual variance empirically. Finally, I wanted to give a shout out to PIPS, which presents a more sophisticated but better performing method of combining gradient estimators like these. With the variance of our gradient estimators addressed, we are now free to unroll longer, obtaining less bias gradients. Sadly, this is still expensive. The good news for us is that these bias gradients can still somewhat be useful, especially early in outer training. In this work, we leverage a curricula over unroll length. Early in outer training, we obtain gradient information faster and thus update faster. We then slowly increase the lengths of unrolls to remove bias. With this understanding, we wanted to see now if we can meta-train some optimizers. In particular, we're curious how much performance we can get when targeting a specific family of tasks. The first step in training a learned optimizer is to pick a parameterization of the optimizer. We wanted something that has good inductive biases, but was also fast to compute. For this, we chose to use a tiny, per-parameter MLP that takes as inputs various features like gradients and momentum values and outputs parameter updates. Next, we need to find a distribution of tasks to outer optimize over. This distribution defines the types of problems our learned optimizer will perform well on. Because the focus of this work is to test performance gains, we chose to use a relatively narrow task distribution. The family of tasks we outer optimize over consists of subsets of ImageNet. We take the 1,000 classes of ImageNet and split them up into an outer train and an outer test set. Each one of these classes contains both training images and validation images. To form tasks, we sampled 10-way classification problems. Unlike the usual few-shot learning setup, each one of these tasks has around 10,000 training images and about 1,000 validation images. The inner model the learned optimizer is training consists of a 3-layer convnet trained with cross-entropy loss. Inner training consists of computing gradients of the training data and using the learned optimizer to update the weights of this inner model. Finally, we need to figure out some way to measure performance of our optimizer. Traditionally, the term optimize means to minimize some training loss. But in reality, people actually care about generalization performance. In this work, we actually trained 2 optimizers, one to perform well on training loss and another to perform well on validation loss. A common point of confusion when we say we outer train on validation loss is that we're overfitting. So I wanted to unpack this a little further. When outer training, we make use of the outer train set of ImageNet classes. In this process, we use both training and validation images from these classes. When applying the learned optimizer, we use the training data to produce weight updates, and then use the validation data to compute how good these updates were, and also to update the weights of the learned optimizer. At outer test time, we make use of the second set of classes. Neither the learned optimizer nor the base model has ever seen any of these images. Additionally, the learned optimizer only has access to training data from these outer test classes. Now to summarize, all that's left is to solve an optimization problem. We seek to optimize the weights of our optimizer, theta. We do this with variational optimization and truncated backprop. We do this optimization over a distribution of tasks, in our case, 10-way classification tasks sampled from ImageNet. We optimize an outer objective, which is either training loss or validation loss. And this loss is computed over inner training, or applying our learned optimizer to a given task. Once trained, we can look to how our 2 learned optimizers perform. What I've plotted here is both training and testing curves for a number of optimizers. We have learning rate tune, momentum, atom, and RMS prop, as well as an extensively tuned atom parameterization. This parameterization tunes learning rate, both linear and exponential learning rate schedules, beta 1, beta 2, epsilon, as well as L1 and L2 regularization. And we tuned it over 2,000 different parameter combinations. Let's first look at the inner training curve to the left. In red, we can see our learned optimizer outer trained to do well on the train objective optimizes extremely quickly, outperforming all the other optimizers by a large amount. When looking at test loss, however, we find our learned optimizer outer trained against training loss actually diverges. This is interesting, but not unexpected. Our goal in machine learning is never normally to achieve zero training loss. If we outer train our optimizer now against validation loss, shown in orange, we're able to achieve lower minima than the other hand design optimizers. Now, I want to particularly point out here that the x-axis is wall clock time. Traditionally, learned optimizers are orders of magnitude slower than their hand design counterparts. We, however, are now able to train simpler learned optimizers that are significantly faster than prior work. Additionally, while not the point of this work, we show our learned optimizer is capable of generalizing. Our optimizer was outer trained on 3-layer convnets on ImageNet and can be applied to 6-layer convnets training MNIST. Despite the task mismatch, we find our validation loss optimizer, orange, optimizes faster than the hand design methods. To conclude, we show that bias and exploding gradients cause problems when meta-training. We present a more stable meta-optimization method using variational optimization and multiple gradient estimators. We demonstrate the utility of these methods by training a simple learned optimizer that's not only faster in wall clock time, but generalizes better than hand design methods. We hope this helps open up the ability to more easily learn learning algorithms and provide a practical alternative to the hand design of algorithms that we do today. Thank you.
Any questions?
Hi. I liked this plot you showed at the beginning where when you have a short horizon, I'd call it, for the outer loop, you actually move the learning rate in the wrong direction, I guess getting smaller instead of larger. I'm wondering if you look at what happens when you do this sort of, I'd call it like scheduling or annealing, where you expand the horizon throughout training. Do you still end up with learning rate going in the wrong direction at the beginning? I would guess so. And then does it like bounce back and recover to find the large learning rate? And then that's kind of weird if that's what happens, because this is like opposite of what we normally do, where we start with large learning rates and then decay them throughout training.
That is exactly what happens. So when you start out with the 2 short truncations, you will diverge, and then as you increase, you will approach the correct learning rate. Yeah.
Cool. Thanks.
So let's thank Luke again. Okay, so now we are going to start with the spotlight talks. So the first speaker is Heng Huang, and he's going to talk about understanding and correcting Oh, sorry. The mystifying dropout. Thank you.
Thank you. In this talk, I will introduce our recent research results on dropout. It's an augmented dropout method. This is a joint work between my group at University of Pittsburgh and JD Finance American Corporation, and also Simon Fraser University at Canada. So the outline for the short presentation is first we will introduce our motivation, and then to show our empirical study for forward and backward dropout. Then I will introduce our proposed method, augmented dropout, and show the results. Dropout is a very popular technique to elevate overfitting problem in deep learning. Now, in many methods, researchers are using dropout method. In community, so far, in our understanding, the underlying reason for dropout to work is one is feature augmentation, the other one is regularization. dropout happens in both forward and backward pass. So in forward pass, basically we can do the we did feature augmentation. In backward pass, we can consider is a noisy gradient can help us improve the performance. Then which path could help us gain more in dropout? So we did quite a lot of empirical study. So first, let's see the definition for both forward dropout and backward dropout. The regular dropout include both directions. So now if we only consider one direction, so for forward dropout, normally we drop features in the forward path. Then we don't drop features at the backward path. So the forward path, we select features, calculate values. Then backward path, we'll pass all the gradient. The other way is the backward dropout. So in the forward path, we don't drop any features. We use all the features. Then when we backpropagate errors, we do the random selection to backpropagate gradient. So that's we consider two subtasks. One is only do the forward, one is only do the backward. So we want to see their performance. So we decide which path really can help us gain performance, gain advantage for dropout. So our observation, we did quite a lot of experiments. So here I show two results. So when for the dropout ratio, typically we select from very small value, from 0.005 to 0.3. 0.3 is pretty large. So let's compare the method. So the plain method means the regular network. For example, we use one is the convolutional neural network implemented by in-cafe turbos. The other one is the ResNet 20. Then the standard dropout, that means we do both dropout on forward pass and backward pass. So forward dropout, we only do the dropout feature in forward pass. Backward pass, we only do dropout for the gradient back propagation. So from this figure, we can see that for standard dropout, actually, they get a pretty good result for most coefficients. But around 0.2, 0.1, usually they get a good performance. But for forward and backward dropout, they have totally different behavior. For example, if we see backward dropout, we can see that if dropout ratio is very large, the performance is very bad. It's poor, much poorer than the standard one and the backward because it's underfitting. So we summarize our observations. So when the dropout ratio is very large, the forward dropout usually get poor result. When the dropout ratios become smaller one, both forward and backward get good performance. When the dropout ratio become very small, the forward also get better results, but backward dropout will get a good result because we can consider if we get a small noise, the gradient still becomes robust. So then we propose the augmented dropout method. So basically, we consider in forward pass, we do a selection features. Then in backward, we further do the random selection ratio. So we can get a better result. For example, in dropout, we do the 0.1 for forward. Backward, we'll do the 0.0002. Then the result, we combine them together, we'll get a better result. So we test on multiple data set. So we use the different ratios for forward and backward. Then we can overall improve the dropout performance. Thank you.
Okay. Next is Taiwan Yong, and he's going to talk about ladder capsule network.
Hi, I'm Taewon Jung, a PhD student at KAIST. I'm going to talk about the new architecture of a capsule network, so-called ladder capsule network, and this is joint work with Youngmin Lee and Hyun Kim from KAIST. Let me briefly talk about the capsule network first. The architecture of a capsule network is similar to other feed-forward network, but it replaces neuron by capsule. That means capsule is the elementary unit in capsule network, and it represents two parts of an entity, the post vector and the probability of existence. This structure of a capsule makes it possible to run equivariant representation. It is easy to understand the caption net structure when you think about the path tree. Taking the example of human face, the whole entity is human face and higher level capsule represented. And the lower level capsule represents the part of human face such as left eye, right eye, and mouth. A goal of capsule network is to capture the partial relationship among lower and higher level capsule, and dynamic routing algorithm is used for this goal. So dynamic routing considers the agreement in higher level space. It first compute the prediction of higher level capsule from all lower level capsule by multiplying prediction metrics. Then it computes the agreement among prediction in a clustering sense. In here, the coupling coefficients are introduced, which represent the degree of contribution of lower level capsule to construct the higher level capsule. They are updated with several iterations, and finally, the output of a higher level capsule is determined by the linear combination of prediction with coupling coefficients. So ladder capsule network focus 2 points in this algorithm. First, it is inefficient to implement routing algorithm using all lower level capsules since some of them can be irrelevant to input data. Second point is the direction of agreement rule. Instead of considering the agreement in higher level space, regression from higher level capsule to lower level capsule can be used for the agreement rule. So these two new ideas are implemented through the pruning and ladder layer. Pruning layer select the k-relevant capsule among all lower level capsules, so it has the role of propagating only relevant capsule to higher level. It also propagates code vector, which is 01 encoded vector to indicate which capsules are selected. And from the output of pruning layer, the ladder layer compute the output of higher level capsule and then regress to k-selected capsule from the higher level capsule. More specifically, the pruning layer select the relevant capsule based on the activity level. The below graph shows the relationship between the activity level, the blue bar, and the coupling coefficient, the red bar in capsule network. As we can see here that the highly activated capsule tend to have a large coupling coefficient, so it is reasonable choice to select the relevant capsule based on the activity level. So from the output of pruning layer, the ladder layer compute the output of higher level capsule, then implement the regression to k-selected capsule. In here, a matrix for linear transformation are required, and for which we use the neural net function of code vector. Comparing with dynamic routing, it does not require multiple iterations, so we have an advantage in reducing computing cost, and we show this through the experiment. So we run the classification task on MNIST and affineness as capsule network does, and also our network underperformed on MNIST, but it shows some significant improvement on affineness. Furthermore, it shows the lower computing cost comparing to capsule network, so we could say that our ladder capsule network is a good alternative to capsule network. Thanks.
Okay. Next topic is Xavier Boutillier. He's going to talk about unreproducible research is reproducible.
Thank you. Unreproducible research is reproducible. What we mean by that is that there is a spectrum of notions of reproducibility, and while some may satisfy, others may not be at the same time. Current focus in deep learning is on one end of the spectrum, and inferential reproducibility is currently neglected, while it is fundamental for empirical research. Suppose we are interested in the ranking of different models, illustrated here as the ordering of the different colors, each representing a different model architecture. The current view in the field for reproducibility is that each time we execute our code, we should exactly have the same ranking again and again. And to do so, we fix every possible sources of variation. But what matters in the end is the conclusion, and this conclusion should not depend on source of variation that we consider irrelevant. According to the terminology of Goodman that we adapted for machine learning, what I just described is method reproducibility. We illustrate it here as different lines representing different execution, always leading to the same ranking. If we leave the source of variation free, then we're moving to result reproducibility, where we aim to reproduce the distribution instead of the precise result. The example we give here is each line is a different initialization of the models, and it can lead to different rankings, but it doesn't matter because what we want to reproduce is the distribution of the rankings, not a precise ranking. At the other end of the spectrum is inferential reproducibility, where we want to reproduce the conclusion using slightly different experimental design, for instance. Suppose the conclusion we want to test is that VGG19 is the best image classifier on natural images. Then we could test this using different data sets of natural images, each line here being a different data set. And if it doesn't hold across all of them, it's not the end of the game, because then we can narrow down our conclusion and test it again using another set of different data sets. And this will help us better understand the model and its relation with the data. We wanted to test how a common methodology in deep learning fares with respect to inferential reproducibility. To do so, we trained 10 different models on 6 different data sets. Selecting the best hyperparameters, we trained them again with 10 different initialization and ordering of the data. I give an example here for the dataset SVHN. Each line in color is a different dataset, and each dot is a test error for a different initialization and ordering of the data. We can see that even if we can reproduce exactly each dot, we cannot make a conclusion simply based on 2 points, because a different pair would lead to a different conclusion. The same applies somehow for result reproducibility, in the sense that even if we can reproduce the distribution of the test performance for different models, we cannot make a conclusion on a single data set, because even if they are similar in nature, they can lead to different rankings. For inferential reproducibility, we aggregated all our results across the 6 different data sets together to make a stack histogram of the probability of having models at different ranks. So here, each column, for instance, here is the probability of having a model at rank 2. We can see that even if MobileNet V2 has the probability of around 0.5 to be at rank 1 in general across all the dataset, it is still not the best one over all of them, because it was often at rank 5 or 9, whereas VGG19 was almost systematically at the top rank 4. This gives a picture that is a lot more nuanced than the common table that we have in our paper, and it suggests that those tables may be a misleading way to analyze our model. To conclude, method and result reproducibility are indeed important building blocks that enables fast exploration and constructive research, but they are insufficient for empirical and confirmatory research, for which inferential reproducibility is fundamental. We believe that all type of reproducibility should have our attention, and not only the 2 first. Thank you for your attention. Please come see us at our poster for more details.
Okay. Next up is Feng Gao. He's going to talk about geometric scattering for graph data analysis.
Yes, thanks. I'd like to introduce our recent work on geometry scattering for graph data analysis. So many data around us can be modeled by graphs, such as social networks, protein-protein interaction networks, and molecules. So to better understand this graph structured data, people try to generalize deep learning methods to graphs. And one of the most successful attempts are graph convolutional networks. So here is a brief review of the graph convolutional networks in recent years. So most of the graph convolutional networks can be divided into 2 types. The spectral JSON, which is the upper part of the figure, and the spatial JSON, which is the lower part of the figure. So this is definitely not a comprehensive survey of all the JSONs, but we can see the increasing interest in studying graphs. So for these JSONs, many of them define convolutions on the graphs, and they learn the filters during the training process. So our question is, can we build JSON in an unsupervised way? So in other words, instead of learning a filter, can we design a filter but can achieve competitive results? So the answer is, of course, yes, but our solution is to generate scattering transform to graphs. So what is scanning transform? Scanning transform uses design and deep filter bank to extract signal features. It's constructed as a cascade of linear wavelet transforms and nonlinear modulus operations. So by applying the low-pass filter 5G here, we can extract the low-frequency information from the signal. And we can then recover the high-frequency information by using the wavelets in multiple layers later. So to generate scanning transform to graphs, we first need to construct wavelets on the graph. Our graph wavelets are defined as the difference between lazy random walks at different time scales. So by choosing the different time step G here, we can construct wavelets at multiple scales. Here's a figure showing the diffusion of our graph wavelet on two different graphs. We can see with the increasing of time step J, our graph wavelet will diffuse to the whole graph. And thus, we can capture the both local features and global features. So with our graph wavelet, we can finally generate the generalized scattering transform to graphs, which we call it geometric scattering transform. So the zero-order features are nothing but the summation of the statistical moments of the signal. By doing the summation, we can achieve commutation invariance, but we also lose the high-frequency information. So in the first-order features, we use our graph wavelet to extract the high frequency. Now, even if we have to do the summation again, we already recover part of the high-frequency information. And then we can recover more by applying another set of graph wavelets in our second-order features. So in this way, we can generate graph representations, and then we can use it for various downstream tasks. In this work, we did 4 experiments. The first is graph classification on social networks. We showed that our geometry scattering method can achieve near state-of-the-art results on classification of these 5 social networks. The second task we did is classification with low training data availability. We showed that with training data reduced from 80% to 20%, it only results in a decrease of 3% in classification accuracy on social network datasets. The third task we did is dimensionality reduction. We showed that geometry scattering combined with the PCA enables significant dimensionality reduction with only a small impact on the classification accuracy. The last task we did is a data exploration of the enzyme structures. We show that the scattering features are sufficiently rich to capture the relations between different enzyme classes. So to conclude, in this work, we generate the Euclidean scattering transformed graphs. We show that the scattering features can serve as universal representations of graphs. And we demonstrate that geometry scattering transform provide a new way for computing and considering global graph features, graph representations independent of specific learning tasks. Finally, I'd like to thank Guy and the CETA team. And thank you. Please come to our poster tonight for more discussion.
Oh, okay.
Okay, so now we have a long talk. It's Kiming Lee, and he's going to talk about robust inference via generative classifiers for handling noisy labels. Please.
Hi, I'm Kim-in. In this presentation, I'm going to introduce new inference method based on generative classifier to handle the noise label. So this is a collaboration with Sang-min Yoon, Ki-bong Lee, Hong-rang Lee, Bori, and Jinwoo Shin. So when we construct a large-scale data set, we usually collect the class label from the data mining technique because it is hard to obtain the class label from the domain experts like human. And because of that, as shown in this example, such large-scale data set can contain incorrect noise label. And it is well known that deep neural networks cannot generalize well from such noise data set. For example, if we corrupt the label of CPAR10 dataset to other class uniformly at random, the tested accuracy of dense network decreases as the noise fraction increases. So this implies that handling noise label is really important problem in classification tasks. To solve this problem, actually there are many kinds of training methods like bootstrapping, loss correction, ensemble method, and meta-learning method. However, such a training method can increase the training complexity. So in this paper, we propose an inference method which can be applied to any pre-trained deep neural networks. Our main idea is inducing a generative classifier on hidden feature space, and by applying the robust inference method to estimate the parameters of generative classifier, we obtain more robust decision boundary from the pre-trained deep neural networks. Here, I want to remark that we also analyze the advantage of such a robust inference method with respect to the breakdown points and generalization error bound. Finally, we introduce an ensemble of generative classifier from the multiple layer of deep neural network to further improve the performance of our method. So actually, that is the short summary of our contribution, and I will talk about more details and experimental results in the next slide. Okay. Then let me explain our main motivation using T-SNE embedding of dense network trained on CPAR10 dataset with uniform noise label. So as shown in this figure, we first found that features from training samples with noise label are scattered in the hidden feature space like outlier. On the other hand, features from training sample with clean label are still clustered even though we trained the networks using noise label dataset. So this implies that if we can induce the posterior distribution from the hidden feature space by removing the outlier, it can be more robust against noise label. So motivated by this, we utilize a concept of generative classifier which model the data distribution Px given y instead of Py given x. Specifically, given pre-trained softmax classifier, we induce the generative classifier by defining the class conditional Gaussian distribution of hidden features. Here, Gaussian assumption is based on our prior work which found that pre-trained features from softmax classifier could be well fitted in Gaussian distribution. Then after defining the generative classifier, new posterior distribution can be obtained as shown in this equation. However, in order to use a new posterior distribution, we have to estimate the parameters of generative classifier first. One naive solution is to compute the sample mean and covariance metrics using features from training sample. However, such naive sample estimator can be highly affected by outlier, which correspond to the samples with noise label in our case. So to minimize the negative effects from outlier, we utilize the minimum covariance determinant, shortly MCD estimator in this paper. So main idea of MCD is finding a subset with smallest covariance determinant because determinants correspond to the variance of the Gaussian distribution. So one can imagine that outliers are scattered in the sample space. So if we find a subset with small variance, it might be possible to estimate the parameter only using the clean sample. Therefore, MCD estimator estimates the parameters of generative classifier only using the samples with small variance. And actually, such MCD estimator has several theoretical advantages compared to the naive sample estimator. The first one is breakdown points, which correspond to the smallest fraction of outlier to make a distance between true and estimated parameter become infinite. Here, I want to remark that high breakdown point imply that our estimator is much more robust to outliers. And as shown in this theorem, it is well known that MCD estimator has near optimal breakdown points, while naive sample estimator has 0% of breakdown points. So with respect to the breakdown points, MCD estimator is much more robust against noise samples. And in addition, we also proved that parameters from the MCD estimator are more closer to the true parameter and has larger interclass distance than sample estimator, as shown in this theorem. So this theorem implies that MCD-based generative classifier has tighter generalization error bound because generalization error of generative classifier is bounded by negative of interclass distance and the distance between true and estimated parameters. So because of that, we can expect that MCD estimator can improve the classification accuracy more than sample estimator. Even though MCD estimator has several advantages, finding the optimal solution of MCD is computationally intractable. So to handle the complexity issues, we utilize a two-step approach proposed by Hubert. First, for each class, we choose a random initial subset and compute the sample mean and covariance matrix. Then using the estimated parameter, we measure the Mahalanobis distance for all training sample. Then we can construct a new subset which contains samples with a smaller Mahalanobis distance. And then we update the sample mean and covariance matrix again. We repeat this step until the determinants of covariance is not decreasing. And after choosing all subset from each class, we compute the final solution using the only using the selected sample from step 1. Here, I want to remark that this greedy method can produce local optimal solutions because finding a subset using a Mahalanobis distance monotonically decreases the determinants of covariance matrix. So let me quickly summarize the contents up to now. So we propose a new inference method which can be applied to any pre-trained deep neural networks. So given pre-trained softmax classifier, we induce a generative classifier on hidden feature space by defining the class-wise Gaussian distribution of hidden features. And we estimate the parameters of this Gaussian distribution using a robust inference method called MCD estimator. Here, one natural question is, what about utilizing the low-level features from deep neural networks? Actually, it has been observed that low-level features can capture the similar patterns from input data, even though data set contain noise label. So this implies that generative classifier from the low-level feature can be more robust against noise label. So to further improve the classification accuracy, we induce the generative classifier from the multiple layer of deep neural networks and combine them into single classifier using weighted ensemble method. So up to now, I explained the main idea of our proposed method. Let's move on to the experimental results. So to evaluate our method, we consider image classification task on CPAR and SVHN dataset. And we also consider NLP tasks like speech tagging and text categorization using Twitter and Reuters dataset. And to make a noise label, we utilize uniform and plim noise label. So in case of the uniform noise, we corrupt the label to other class uniformly at random. And in case of the plim noise, we corrupt the label only to the specific class. And in order to verify the stepwise improvements of each component, we incrementally apply our method using RES network trained on CPAR10 dataset with 60% uniform noise. First, I want to remark that MCD estimator improved the performance compared to the sample estimator by removing the outlier. So when we measure the fraction of clean samples from each estimator, we indeed found that MCD estimator can select clean sample more effectively than sample estimator. So because of that, MCD can improve the classification accuracy compared to sample estimator. Next, I want to remark that ensemble method also improved the classification accuracy as shown in this table. To analyze the effects of ensemble method, we measure the layer-wise accuracy of generative classifier as shown in this figure. So x-axis corresponds to the index of layer, and y-axis corresponds to the classification accuracy. And one can note that generative classifier from the low-level features are more robust against noise label. So because of that, ensemble method can improve the classification accuracy as shown in this table. And here, one can have a concern that such generative classifier can degrade the performance on the clean data set. But we found that this is not a case for our method because we have a lot of training data. Next, we also compare our method with prior training method. When we apply the special, so here is the tested accuracy of Let's network. And when we apply the special training methods like bootstrapping, port, and D2L, the test performance of the softmax classifier can be improved as shown in this figure. However, we found that our method still outperforms this softmax classifier when our method is applied to pre-trained model. So this implies that more higher accuracy can be achieved by combining our method with other prior training method. So as shown in this figure, our method can improve the performance over other training methods like co-teaching and GSE method when you consider other types of noise labels like film noise and NLP dataset. Actually, we have more results, so please check our paper for more detailed results on various dataset and training method. So up to now, we consider some synthetic noise, but as a final result, we also consider more realistic case using machine-generated labels. First, we train a classifier using small number of labeled dataset. And using this weak classifier, we generate pseudo-labeled dataset as shown in this figure. Then one can expect that such dataset contain noise label from the misclassification. And somewhat interestingly, we found that noise level from the weak classifier are more realistic as shown in this confusion graph, where the node corresponds to the class and edge corresponds to the its most confusing class. So for example, similar to the human, cat is confused with a dog, but not with a car when you generate the labels using a weak classifier. And as shown in this table, as shown in this figure, our method still outperforms the softmax classifier with various training methods. So this implies that our method can be working well even in the more realistic case. Okay, so let me conclude this presentation. So to handle the noise label, we propose a new inference method based on the generative classifier with robust estimator called MCD estimator. And by applying the ensemble method from the generative classifier from the multiple layers, we further improve the generalization ability against noise label. And we believe that our method can be useful for many other machine learning applications like depending adversarial attack or detecting out-of-distribution sample. So we have a poster session today, so if you want to know more about our paper, please come to our poster session. And thank you for your attention. Yeah.
Okay. It's time for a couple of questions. Okay, so I'll ask a question. So did you try to compare your minimum covariance determinant with like classical notions of robust statistics, like for example like medians, like to try to eliminate outliers by using medians or stuff like things like that?
Actually, we tried, but we found that MCD estimator is more effectively improved the classification accuracy, and we also have a results on our paper. So yeah.
I have another question as well. Sorry. So if I understand correctly, you don't backprop through. So
Yes.
this is just a post-processing thing that
Yeah.
you do. Did you consider also, I mean, including this into the loop of training?
Oh, okay. So actually, we can consider something like a semi-supervised learning to further improve our method, but we didn't try yet. So maybe, yeah, it can be a more interesting direction to extend our method. Yeah.
So let's thank the speaker again. So next up is Daniel Kang, who's going to talk about learn intermediate representation training for model compression.
Great, thank you for the introduction. So I'm Daniel Kang. This is joint work with Animesh Karatana and Professors Peter Bayless and Matei Zaharia as part of the Stanford Dawn Lab. In this talk, I'll be describing LIT, Learned Intermediate Representation Training for Model Compression. So our goal is to compress models, and basically the goal here is to take a large model and turn it into a smaller model that has high accuracy. In this talk, I'll describe how to achieve higher compression for modern deep networks which have repetitive sections. In this plot I'm showing here, I'm showing the number of layers versus the accuracy of our method compared to a variety of baselines, and we'll describe how to achieve these improved results. So first, to take a step back, there's been a lot of prior work that has shown that deep networks can be compressed to reduce inference costs. So for example, in deep compression, you take a trained network and remove parts of the network to basically get a smaller network. And in knowledge distillation, you take a teacher model, and you use the outputs of the teacher model to train a student model using entropy-based loss. However, these methods are largely architecture agnostic. In other words, they don't take advantage of the fact that modern deep networks have a lot of structure to them. So what do I mean by this concretely? On the top of this diagram, I'm showing a resonant 110, and on the bottom, I'm showing a resonant 56. Both of these models have 3 sections, which have 18 and 9 residual blocks, respectively. And in the green, I'm showing where the outputs of these sections are downsampled, and importantly, they have the same width here. And so we asked the question, given the structure in these modern deep networks, can we use this somehow to compress deep networks more effectively? And so we show the answer affirmatively. And so the first thing we do is we we penalize the deviations in intermediate representations of architectures with the same width. So for example, here in the sections in green, we use the L2 loss to penalize deviations from the student and the teacher model, in addition to the standard KD loss. We found that this actually underperforms standard KD, though. So in addition, we use one more trick, which is to take the output of the teacher model's previous section as input to the student model's current section at training. At test time, you can just use the student model as is. Putting these two together can achieve up to 4 times compression on CFAR10 by taking a resonant 110 to a resonant 34. This outperforms standard knowledge distillation and hint training, which also uses intermediate representations, but was designed for older neural networks. It also performs training from scratch. Furthermore, we show that LIT can compress a variety of other types of models, but one I want to highlight is actually that LIT can compress star GAN, which is an image-to-image translation GAN. The structure of star GAN is that there's a downsampling section, a repetitive section which has residual blocks, and then an upsampling section. In this experiment, we take a teacher model which has 18 layers, and we compress it to a student model which has 10 layers. The model trained with LIT outperforms the teacher model, and in fact all the alternatives, both in inception score and in FID score on this particular task. Furthermore, it might be hard to see on the slides here, but please find this other poster if you're curious. The student model also outperforms the teacher in qualitative evaluation. What I'm showing here highlighted in the red is that there are artifacts in both the teacher model and the model trained from scratch with 10 layers around the headband, which is not present in the student network. So in conclusion, neural networks are becoming more expensive to deploy, and LIT is a novel technique that combines both intermediate representations and matching outputs. And this can improve training and give 3 to 5 times compression for many tasks and outperform a variety of baselines. If you have any questions, please find us at our poster in Pacific Ballroom. We're poster number 17. Thank you for your time.
Okay. Next up is Nicholas Frost, who is going to talk about analyzing and improving representations with the soft nearest neighbor loss.
Hi, yeah, I'm Nick Frost. I'm going to be talking about work done at Google Brain with myself, Nicholas Poppernow, and Jeffrey Hinton. So our work centers around a loss function that we call soft nearest neighbor loss, which is down there at the bottom if you want to read the equation. The loss is defined over labeled data points and can be used in any space. So it can be used in image space and representation space, just needs labeled data points. And it can be thought of as an approximation of how good a k-nearest neighbor classifier would do in that space. So on the slide, we have 4 examples of 4 different spaces with 4 classes denoted by color and various values of this loss. So we can see that when those classes are all mixed up together, when the classes are really entangled, a k-nearest neighbor classifier would do quite poorly, and it has a high soft nearest neighbor loss. And if you look at the bottom right, there's a very low soft nearest neighbor loss, and that means that a k-nearest neighbor classifier would do quite well because the classes are very disentangled. So our paper just focuses on all the various things you can do with this loss function. The first of which is you can use it as a tool for understanding the progression of discriminative learning. So the point in a discriminative model is to separate all the classes into eventually fully separate classifications. And we can see that different layers in a ResNet trained to classify CFAR10 progress in different ways when measuring the soft nearest neighbor loss in the internal representations. So we can see that the final layer decreases soft nearest neighbor loss almost monotonically throughout training. So it's separating the various class manifolds, and it does that consistently during training. We can see that earlier layers initially separate the classes, and then they kind of mix them back up again as features are co-adapted and used to represent things in multiple classes. We can also use this as a tool for understanding the progression of generative training, in which a generator is trying to entangle the generated data with the real data. So here we can see that soft nearest neighbor loss increases over training as the samples from a CFAR generator become more realistic and start to look like they're coming from the real distribution. So a large part of our paper focuses on this loss function as a regularizer. We explored what happens if you try to train a model, so backpropagate classification, cross-entropy error to train a classifier, but you add a penalty into the intermediate representations to say keep all the labels, all the label manifolds, the class manifolds entangled, so have high soft nearest neighbor loss. Now you might think that this is the opposite of what a classification network ought to do. It should be separating those things, and that's exactly right. And we add a penalty that says do the opposite of that, keep all the classes mixed up in your representation space. And we see that this turns out to be a decent regularizer. So we get better generalization and less overfitting when we add this in as a penalty. The meat of our paper is about networks that have been trained to entangle the manifolds using the class manifolds using the soft nearest neighbor loss. Sorry, this thing is jumping back and forth here. Okay, I'll try to keep it there. So what happens if you use that? If you use networks that are trained to entangle things? Yeah. I'm going to give an overview of everything that's just been done using all the slides really quickly. I'm not sure what's up with that. OK, don't look at the slides, and I'll just keep talking, and we can try to figure this out. So essentially, we're looking at something called the deep KNN classifier, which is something that was established earlier to detect adversarial examples. Oh. OK, there you go. Here you go. Here's a good diagram. And the deep KNN classifier just instantiates a KNN classifier at every layer of a neural network, and then it looks at the nearest neighbors of every sample at test time. And it looks at the statistics of the nearest neighbors to try to figure out when you've been given an adversarial example or when you've been given something from the true data distribution. And it turns out that if you train a network to keep all the classes very entangled, this strategy for detecting adversarial examples and outliers works a lot better. And we get much better estimates of uncertainty and credibility from the deep KNN classifier. So if you want to know more about this strange loss function and all the weird things you can do with it, come to the poster session number 18. Thanks.
So next up is Jonathan Bird from Carnegie Mellon, and he's going to talk about what is the effect of importance weighting in deep learning.
Yeah, so importance weighting is a classic technique that's behavior is very well understood for simple and linear models, but it's been popular recently to combine with deep learning. And there's recent theory that shows that linear models, when trained on linearly separable data to optimize cross-entropy loss with SGD, the weights converge in direction to the max margin solution. So consequently, the learned decision boundary depends only on the location of the data points and should be unaffected by any sort of reweighting. And recent work also provides some empirical evidence that suggests that a similar effect might hold for modern deep neural networks, which can shatter real-world data sets. So this contradicts with the fact that people use these two techniques together in practice and motivates us to sort of dig empirically into what exactly happens in this situation. So we look at, we run experiments on a few different data modalities with popular architectures, including residual networks and pre-trained BERT transformer language models. And we weight examples based on their label and look at how that affects learned decision boundaries. So one of the main findings that we find is that the effect of importance weighting diminishes over successive training iterations. So while early on in training, we find shown on this slide, very simple 2D toy data, we find that classifiers partition more of the sample space to the class with higher weights on the examples. However, in the limit, models seem to converge to have roughly the same decision boundary. And that's differently weighted models, the same decision boundary. And we find that we also find this effect when training convolutional networks on CFAR images, in this case just cat and dog images. So we look at the fraction of test images that are classified to a particular class, both cat and dog test images as well as off-manifold images from the other 8 classes. And we find a similar effect where models will classify much more test examples as the class with higher weights initially early on in training, but as training progresses, this effect seems to disappear and they classify roughly the same ratio of test examples. And when explicitly correcting for label shift at test time on multi-class CFAR, we find that the accuracy actually decreases similarly over training time. And we find similar results to these as well on text data. And so another finding is that L2 regularization restores a lot of these effects of importance weighting and dramatically sort of reduces the speed of this diminishing effect. And this may be because here we are penalizing the large norm solutions that minimize cross-entropy loss. And this aligns with some of our theoretical motivation. And so the big takeaway here is that we find that the effect of importance weighting on deep networks is very heavily dependent on lots of hyperparameters that you'd like to think shouldn't really be related. And if you'd like to hear more about this or have any questions, come by poster 19 tonight. Thank you.
So last spotlight of this session is Simon Kornblith, from Google Brain, and he's going to talk about similarity of neural network representations revisited.
Hi, I'm Simon Kornblith. I'll be presenting our paper, Similarity of Neural Network Representations Revisited. This is joint work with Mohammad Narouzi, Hong-Lok Lee, and Jeff Hinton. So the motivation behind this work is that we want to understand neural networks. But because when we train a neural network, there's an interaction between a learning algorithm and some training data, and we don't understand the structure of that data, that's why we're training the neural network in the first place, there's some limit to what we can understand about what the neural network is going to do just by understanding the learning algorithm alone. So ultimately, we need some way to look inside the trained neural network. And one approach that's been very successful in neuroscience, which is what my background is in, is to think about comparing its representations. So what is a representation? Well, for the purpose of this talk, a representation is just a matrix. And this matrix holds the activations of some set of neurons to some set of examples. So the examples are the rows of this matrix, and the neurons are the columns. And because we're thinking about comparing representations, we need to think about two matrices, X and Y, which represent two different sets of activations from two different layers, possibly from two different neural networks, to the same set of examples. So the next question is, should we be thinking about comparing the features of these neural networks, or should we instead do something more complicated maybe and think about comparing the similarity structures of the examples? So it turns out that if you use a dot product to measure similarity, then measuring similarity between the features is actually the same as measuring the similarity of the similarities between examples. So more mathematically, we could imagine taking the dot product between all possible pairings of features, squaring these dot products and summing them up, and we'll get the same result as if for each representation separately, we take the dot products between all possible pairings of examples. This gives us two vectors, and we then take the dot product between those two vectors. So in practice, we want to normalize the similarity index so that it's invariant to isotropic scaling, and this gives us a number between 0 and 1. And this is a relatively simple idea that's been discovered several times in the past. So in particular, centered kernel alignment is kind of a generalization of this idea, where we can also think about replacing the dot product or linear kernel with a different kernel that allows us to emphasize different aspects of the representation when we measure similarity between the examples. So having come up with this similarity index, how do we know if it's a good idea or not? So we propose a very simple sanity check just to verify that a similarity index for neural network representations actually makes sense. And the idea is basically we have two neural networks that are architecturally identical but trained from different random initializations. And if we take a layer from network A, we want it to be the case that the most similar layer from network B is the architecturally corresponding layer. So if we do this with centered kernel alignment, we get plots that look like this. Here, the X and Y axes are the layers of two different neural networks trained from different random initializations. And the colors represent the magnitude of the similarity. So you can see that the diagonals here are brighter than the off diagonals, and that means that the architecturally corresponding layers are more similar than the non-corresponding layers. So we can also do this for the plain 10-layer CNN with other methods that people have proposed to measure similarity of neural network representations, which are based on canonical correlation analysis. And we see that centered kernel alignment works, but these other methods do not pass this sanity check. So finally, you can ask, this is an interesting idea, but how is it useful in practice? And we're still working on that question, but here's something that we came across kind of accidentally, which we think gives some interesting insight into how neural networks work. So we took our 10-layer network on C410, and we make it deeper just by adding additional layers. So we repeat each layer twice or more times than that. And it turns out that if we make the network really deep, the accuracy of the network actually goes down. So why does the accuracy go down? Well, if we compute centered kernel alignment, this time between layers of the same neural network, we get plots that look like this. And you can see that at the shallower depths, the representation is kind of iteratively refined. But for the very deep network, all of the later layers of the network are very similar to each other. And we can validate that centered kernel alignment gives us an accurate representation of how the neural network operates by training a logistic regression classifier on these layers. And again, we see the accuracy doesn't go up in the second half of the network. Thank you.
Okay, so this concludes this session. So let's thank again all the speakers.